Building directly on this moment of intellectual readiness, Jevons demonstrated how diminishing marginal utility could be expressed with striking clarity through his logarithmic utility function, where x represented the quantity of a good consumed and k the good's intensity of utility or the strength of feeling it evokes. Differentiating with respect to x yields an equation for marginal utility, showing that additional pleasure gained from each new unit steadily declines as consumption increases. Whenever you see the phrase marginal revenue, marginal utility, the word marginal means slope. And so we have slope of utility. It's the change in utility over the change in x. And when the utility function is k times the natural log of x, the derivative of the natural log of x is 1 over x. So we have k divided by x. To bring Jevons' abstract theory to life in a vivid Victorian context, imagine the good in question as tea, a beloved staple of 19th century England. And suppose Jevons assigns the coefficient of utility k equal to 10 to capture the strong intensity of satisfaction tea provided to consumers of his day. Using his logarithmic utility function, Jevons understood that as consumption approached zero, utility would plunge toward negative infinity, signaling an absence of satisfaction so extreme it lay beyond meaningful measurement. Rather than adjusting the utility function to force utility to equal zero at zero consumption, he deliberately accepted this mathematical limitation because his goal was not to describe total utility at theoretical boundaries, but to clearly express the laws of diminishing marginal utility through the elegance of the derivative. For Jevons, utility was a relative psychological magnitude, a reflection of human feeling and desire, and his focus remained on how satisfaction weakens as consumption increases, allowing him to illustrate with precision how each additional unit of tea yields progressively less pleasure even as total enjoyment continues to rise. Substitute k in the values of x into its utility function and its derivative to complete the table below. I've already recreated the table in Excel here with cups of tea, total utility, and marginal utility as headers. I'm not going to enter anything into here and here because this is negative infinity and that's positive infinity. And to get a good feel for why that is, let's just type equal, k in my case was 10. So 10 times the natural log of x equals, we get an error message, and I'm going to address that in a second. And then the marginal utility was the derivative of total utility, and that was the constant k, which in my case is 10, divided by x. Again, we get error message. So the best way to think about the negative infinity and the positive infinity here and here is to replace this with a small number. I'm going to try 0.000000001. That's pretty close to zero, right? I'm going to change all of these from scientific notation just to regular number notation. And then I'll double click this to show you what's going on here. So when x is really close to zero, total utility is a large negative number and marginal utility is a massive positive number. As I take this smaller and smaller and smaller, total utility gets bigger and bigger and bigger in a negative sense, and marginal utility gets much larger as well. So when there's 200 zeros between the decimal point and 1, total utility is now negative 4,605. And marginal utility is some massive number that we can't even show anymore. We're not going to calculate these two, but we can calculate total utility and marginal utility for cups of tea from 1 to 9. And it was, for me, 10 times the natural log of x, in this case 1. I'm going to press enter, and then 10, my constant, divided by 1. Then I'm going to drag these down, and I need how many decimal places? 3 decimal places. So I'll type in 0, and then this one is 10, 6.931, 5.00. I went through and I filled in all the values for the table. The values in the above table appear to create an inconsistency. The change in total utility between consecutive values, such as from 1 to 2, Our utility changes by that difference, but our marginal utility is 10 or 5. This change is between that value and that value. Jevons would explain this by carefully distinguishing between the pleasure from a whole extra cup of tea, moving from 1 to 2 cups, and the pleasure from an infinitesimally small sip of tea. When consumption rises from 1 cup to 2 cups, total utility increases from 0 to 0.6931. The former represents the satisfaction of drinking the entire first cup of tea, while the latter represents the satisfaction gained from drinking the entire second cup of tea. But Jevons' marginal utility did not measure that whole jump. It measures the pleasure from a tiny, almost immeasurable sip at a precise level of consumption. At exactly 1 cup, the marginal utility is 10.000, meaning a very small sip taken at that moment would feel extremely satisfying. At exactly 2 cups, marginal utility has already fallen to what? 5. And that means a tiny sip taken after the second cup is much less exciting than it was when the person was at 1 cup and took a small sip. The increase in total utility from drinking the first cup to drinking the second cup is the difference in these two. This minus 0, 6.931. Naturally, it lies between these two intensities, 10 and 5, because the full second cup is consumed over a range in which desire steadily weakens. In simple terms, Jevons viewed marginal utility as the momentary strength of craving for the next unimaginably small sip, while the change in total utility reflects the satisfaction of drinking the entire additional cup. I think the best way to illustrate what we're trying to get at here is we're going to take the differences in X and the differences in utility. This is the calculus method of calculating marginal utility. What I'm going to do here is I'm going to show you the micro principles method for calculating marginal utility. And we have to start at 2 cups of tea. The change in X is 1, from 1 cup of tea to 2 cups of tea. And that's the case for all these consecutive pairs. 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, and 8 to 9. When we go from 1 cup of tea to 2 cups of tea, what happens to utility? Our utility changes from 0 units of utility to 6.931 units of utility. And now as I drag this down, you can see the change in utility for each additional cup of tea is diminishing. When I divide this by that, I get a measure for marginal utility where the change in X is in units of cups of tea. When using Jevons' calculus version of marginal utility, the change in X is a really tiny sip of tea when we're at 1 cup of tea. When you have consumed 1 cup of tea, and you take a small sip, we're talking about a very small change, and that produces a change in utility of 10. So when we're using the calculus version, we have these really tiny increments of t. But when using the discrete version of marginal utility, we're talking about a much larger increase in x. In this case, each of these changes in utility is a result of drinking an additional cup of tea.